Hello, class. All right, so we're going to talk about rotational kinematics. So basically what we're going to do, let's say very concrete example. Say we have, this could be like a wheel or something that is spinning. And we want to be able to describe the motion of this object. So I'd say this is a wheel and the axle is fixed in place, but the wheel is just spinning in place. So it's moving around. And we want to be able to describe things like, like how fast is it rotating? Is the rate of rotation speeding up or slowing down? Or like what angle did this rotate through? So we can draw a reference line here. And picture as this wheel is spinning, this line is spinning around with it. And in some time interval delta t, actually, let's start out, say we center this on an xy plane, and say, just as standard, that on the positive x-axis, we define the angle to be 0. And so we can define the angular position of this reference line. We can describe that with the angle theta. So position we use the variable theta. Now, it's moving, we're assuming. So let's say at time t1, we can start it anywhere, but since I start anywhere, but say at t1, it's at a location theta 1, which in this case is 0, but it can be anything. And then at t2, this reference line is at a different location, and the angle that it rotated through, now let me change this. Let's say at t1 it's here, so we'll call that theta, and then say at t2 it's over here. And we call this angle that it rotated through, we call that the angular displacement, which is the change in the angle. So angular displacement we use this variable delta theta. And that would just be the displacement over this time interval from t1 to t2. And again, it doesn't matter how long it took. It's just, we know we started here and we ended here. Now, I will say one thing though. When we're looking at kinematics in one dimension, we had, like say we're at x1 and x2. I said it doesn't really matter how you get from x1 to x2. In this case, we have to be a little bit careful though, because, like just as an example, say you start here and you go and loop around and end up at x2. Your displacement is just, that distance from x1 to x2. That's your displacement over that time interval. It's a little bit different in the case of rotations. As I said, it doesn't matter the details of what happens in between. But with angular motion, it does matter if you complete a circle. So let's say we started here and ended up here. That would be our displacement. If the wheel made another complete rotation and then, ended up here, that angular displacement would be a little different than just this short one. And so again, we're kind of dealing with one-dimensional motion again. Like if you just keep rotating in the same, your angle will keep on increasing, even though you'll keep coming back to the same place. Whereas that's a difference in linear motion. If you just keep going in one direction, you never come back to where you started. So your angular displacement, it's not just the starting and ending point. It also matters, if you complete a cycle or not. But yeah. So, but again, kind of the same as in this case. You could say start here, your reference line is here, and then you rotate through an angle and then come back. That displacement will be the same as if you just rotated directly through that angle. Just when you complete a circle, you can end up back where you started, which is not the case here. But, yeah, again, time is not a factor. It only matters where you started and where you ended. But we can get a measure of how fast this is rotating, this object, with what we call angular velocity. And we use the symbol omega. That looks just like a W, but it's a Greek letter omega. And we define this to be the displacement over the time interval. And I left a gap there because we have the same issue we had in Chapter 2 in defining velocity. This would be like your average angular velocity. But for a more precise measure, we'd have to take the limit that delta t goes to 0. So we make this distinction between an average angular velocity and the instantaneous angular velocity. Where, yeah, if we just write omega, that's the instantaneous. And finally, if the angular velocity is not constant, we have an angular acceleration. Which we use as Greek letter alpha. And I'll just put that limit in right away. That's the rate of change of angular velocity over time. So what we've done is we've described things just like we did in Chapter 2. And I want to actually make a table just to compare these. So we have linear and rotational motion. This marker's pretty much done for. Okay, so we have position, displacement, velocity, and angular velocity. So in linear motion, we had x, delta x. I'm not going to write the limit here. Well, maybe I can fit it. And then for velocity, it's displacement over time. And for acceleration, we have the change in velocity over time. For angular motion, let me just write this down. Okay. So we're just defining things for rotational motion now. And things look very similar to what we did in Chapter 2 with linear motion. Basically, mathematically, these two things are identical. We just have different variables, but the relation between these variables is exactly the same in both cases. And so if you remember back in chapter 2, we had a goal. Where's this? Our goal is, let's see if I can fit it over here. You know, if we are given, we have a constant acceleration, and we were given the initial position and the initial velocity and the constant acceleration, and our goal was to find the position and velocity as functions of time. Because if we have that, we know everything about the motion of this object. So again, we're restricting ourselves in chapter 2 to one dimension and constant acceleration. And now our goal in chapter 8, when we're talking about rotational motion, is given a constant angular acceleration and given the initial angular position and angular velocity, we want to find the position, angular position and angular velocity as functions of time. And what I'm going to do is just write down the answer. And the reason is we've already solved it. The math doesn't care what we call our variables, and it doesn't even care what these variables represent. The relation between these is exactly the same. And so I can just write down the solution here. So first off, I want to reinforce the idea that this only applies, these equations are only valid if we have a constant angular acceleration. So that's very important. But then we have the solution, which is exactly the same as what we got in chapter 2, where all we do is we replace x with theta, v with omega, and a with alpha. And we get the exact same equation, or set of equations. And again, these are the basic solution to this problem. Now, we have a third equation in kinematics, and again, we get the same thing. We also had this equation, v squared equals v naught squared plus 2a delta x from kinematics. And we got that by taking the velocity equation and solving for t and then plugging it in the position equation. And again, we can do the exact same thing. We can solve this equation for t, plug it in here and here, do the algebra, and we will get this result. So we're not going to go through and rederive things, because if you wanted to, you could literally go back to chapter 2 and do the exact same algebraic steps just with these variables, and you get the exact same solution. Okay, now chapter 2 we were talking about linear motion, one-dimensional. And now we're talking about rotational motion. And we know that things like position, velocity, and acceleration are vectors. So what about these variables? Are they vectors? Like, is theta a vector? Let's start with that. Or no, not theta itself. Let's ask the question, is delta theta a vector? Is angular displacement a vector? You can kind of demonstrate this by rotating this book. So here's our physics book, older edition, but same stuff basically. So let's say I rotate this 90 degrees clockwise. It ends up like this. If I rotate it 90 degrees counterclockwise, we rotate it through the same angle, but we got very different results. And so, well, the magnitude is 90 degrees, and direction definitely matters. And so that looks a lot like a vector, but actually it's not. or more precisely, angular displacements in general are actually not vectors. And the reason why, let's go back and look at just our basic vectors. Yeah, we use them to represent things that have magnitude and direction, but not everything that has a magnitude and a direction is a vector. And to explain why, let's say we have two vectors, A and B. And we can add those, and the sum is A plus B. Now, if we did B plus A, we'd just do this. We have B first, and then A, and we get the exact same result. So we can say that A plus B equals B plus A. That is a general property that vectors have. That the commutative, yeah, that one's commutative. I always mix that up with the associative property, but yeah, vectors commute. Do rotations commute? And at first glance, it might seem like they do. Like say I rotate it 90 degrees one way and say 40 degrees the other way. So let's say, let's say like 90 and then 40. It ends up something like this. So we can think of this as 90 and minus 40. Now if we did like minus 40 and then 90, we'd end up in the exact same place. And so this commutative rule would work. But this is a special case because I'm rotating this book about a fixed axis. In general space, you can have rotations in any direction, and it turns out that these rotations do not commute in general. So let's look at an example. Let's say rotation A is going to be like this, 90 degrees clockwise, about this axis going through the book here. And then let's say rotation B is this rotation, about like a vertical axis. So I'm going to do like A plus B. So remember, this is A, that's B. So A plus B would look like this. So the book is facing you, top of the book is here. I'll start it in the same orientation and do B plus A, and we get a very different result. And so, in general, if we stick to rotations in one plane, then they behave just like vectors. But if you allow rotations about an arbitrary axis that are like just three-dimensional vectors, no, not. Angular displacements don't follow that commutative property, and so they do not actually count as vectors. Now, angular velocity now this is an angular displacement over time, and if angular displacement isn't a vector, you'd probably guess that angular velocity is not a vector either. However, angular velocity actually is a vector. And the reason why is because, I mentioned rotations about different axes, the order matters. And we got very different results considering two 90-degree rotations. But if I pick two smaller rotations, they'd end up in different orientations, but they'd be a lot closer together. And the smaller the rotations are, the closer it comes to following this commutative rule. And it turns out when you take the limit that delta t goes to 0, the commutative rule holds up. And so omega is a vector, as long as we're talking about the instantaneous velocity. And so it has a direction. Now, here we've got a nice circular object here. Although it's maybe here. If I hold it up, you can see writing on it. So again, it's rotating. It has we can represent this with that angular velocity with a vector. Question is, what direction is this vector? Like, how do we find a direction for a rotation? So if I draw it on the board, here, let's say this object is rolling like this. So we have an axis here. Say it's rolling this way. So it is an angular velocity vector. How can we describe this, the direction? And a very common question in a normal classroom, someone will say, well, it's rotating clockwise. But clockwise isn't like a direction in three-dimensional space. We want to define angular velocity as something we could represent with an arrow pointing in space. And so we use something called the right-hand rule. So again, here's our object. Say it's spinning like this. First off, we can define a unique direction. This is a plane. Even if this was, say, a mass on a string. So it's not like a disk, but we have a mass going around the string. The circle that it fills out exists in a plane. And so we can define a unique direction as being perpendicular to the plane. So the angular velocity vector is on this line coming, through the axis, like perpendicular to the plane. The problem is there's two directions. And so we have to be able to pick one. And to do that, we use something called the right-hand rule. What you do is you curl your fingers. It's called the right-hand rule, so you use your right hand. You curl your fingers in the direction of rotation, and your thumb points in the direction of the velocity. So here, omega would be into the board. Where if we had it rotating counterclockwise, again, just curl your fingers counterclockwise, thumb points out of the board. And that gives a unique direction for angular velocity vector. Now, we're not going to use that too often. But I think it's worth mentioning for two reasons. One, there is an application we're going to look at later where we talk about where we need to know the actual direction in three-dimensional space. It's an interesting enough example that, just learning the right-hand rule is worth it, probably worth it, just for that example alone. But beyond that, if you take 122, you're going to have to get very used to the right-hand rule. Not at first. Once you start talking about magnetic fields, the right-hand rule is critical there. So I think seeing it now is definitely worth it. Okay. So, yeah, we've got our rotational kinematics here. Oh yeah, so coming back here, I said we're not going to use this very often. Most of the applications we consider, like almost all of them, are going to be rotations about a fixed axis. And in that case, for the direction of angular velocity or rotations or whatnot, we can just say that clockwise or counterclockwise to describe directions. Because if you have a fixed axis, that's good enough. And by convention, we typically say that counterclockwise is positive and clockwise is negative. So we can describe this angular velocity as either into the board or just negative, because it's going clockwise, out of the board, counterclockwise, or positive. And again, this is naturally the way that we measure angles anyways. Well, maybe not naturally, but just by convention. This is the way you've always learned it, where you measure angles counterclockwise is positive. So like that would be, like we start out, quadrant 1, 2, just going counterclockwise is what we accept as our positive direction. Okay, now I'm actually going to pause here for a second. I'm going to try to fix the lighting. It seems a little dark in here. So I'm going to see if I can fix that. And then we're going to talk about, maybe we can do an example of kinematics. But then we're going to talk about like how we can relate, like say we have this point on this spinning disk, like this point has a velocity, you know, how does that depend on how fast this thing is spinning? And we know it's accelerating as well. This point on the edge of the wheel is accelerating. So we're gonna deal with things like velocity and acceleration of a point on a spinning object. And then talk about a very important application, which is rolling, like a wheel that's rolling across the ground. But I do want to kind of fix up the lighting here, so this would be a good point to kind of take a break. Right. So we're going to look at, let's say we have an object that is rotating, say in this direction, and let's look at a point, could be anywhere on this object. Let's say it's a distance r from the center. So here's the center here. And this object has a tangential velocity. So it'd be perpendicular to that radius. And you know, it's moving, it's rotating this way. If it was rotating the other way, velocity would be downwards. And we want to relate these variables here. This tangential velocity, the radius, and the angular velocity. So the idea is, let's look at a small rotation. So it's rotating, let's say it rotates through this angle delta theta, where omega is the rate of rotation. And if we look at this point, the distance that this traveled, remember our equation for arc length? Where the arc length is equal to the radius, actually I'll write it r delta theta to match with our picture here. So the distance at this point travels, we'll call that s, that's equal to r delta theta, provided that we're measuring our angle in radians. And the tangential speed is just distance over time. So that would just be s over delta t. So that would be r delta theta over delta t. And remember, delta theta over delta t is omega, our angular velocity. So we have this result here. Actually, I'm going to erase this and just say, just put the radians part up here. So we had s is equal to r delta theta, and then the tangential velocity is r omega. And the reason I wrote this is because to get this result here, we use this one. And so if this one's only valid in radians, so is this equations. So let me write down this conversion factor as well. So 2 pi radians is 360 degrees, or 1 revolution. So these are different ways we can describe angles or angular displacements in radians, degrees, or revolutions. And revolutions are actually frequently used. Like if you look at your car, you know, it measures the engine in like revolutions per minute. And so that is a unit that will come up. And so you can convert that to either degrees or radians. Now, when we're dealing with kinematics, it doesn't matter what units you're worried about, because it's always going to work out. As long as you plug in the units when you need them, you're fine as long as you are consistent with the units here. If you have degrees or revolutions, you can plug those in. Everything works fine. But if you're ever going to use either of these equations, you simply must be in radians or it's wrong. And if you're ever not sure, safe bet is just convert to radians. So you don't always have to, but you'll never go wrong converting to radians, provided you do that correctly. Not that hard to convert, just all the factors you need are there. Okay, now we can also talk about the acceleration. Now, we know there's an inward acceleration of this particle because it's moving in a circle, but what if the velocity is changing? We can talk about a tangential velocity as well, which would be the rate of change, or tangential acceleration would be the rate of change of tangential velocity over time. So we have A is delta tangential velocity over time, and if we plug this in, we have delta r omega over delta t, and r is a constant here. We're looking at an object that's a fixed radius from the center. And so we can take that out of this. When you have like a product of two things, one's constant, one is a variable. When you use delta thing, you can just take that constant out. And I'll actually show that off to the side. But, just to finish this, the tangential acceleration is equal to r, well, it's r times delta omega over delta t, or r alpha. Now, just to be clear, in case this isn't obvious, let's look at delta rw, where r is a constant, but omega is not. So we're taking the difference, delta, so that would be r times omega final, minus r times omega initial, and then we factor the r out, and omega final minus omega initial is delta omega. So like going from here to here, there's a couple steps involved, a little shortcut, just pull that r out. And again, this happens fairly often, so you get to just recognize that you can do that. So let's add this here as well. And again, this equation was derived from this one, which was derived from S equals r theta. So you have to be careful to only plug things in when you're dealing with, or make sure you're in radians if you're going to use those equations. Okay, now technically these equations might not be, well, let's look at a potential problem with using these. It might be better to write these equations a little differently. Like S equals r theta, I've kind of considered doing this before, but writing the equation like this, like S equals r theta over radians. Now, why would we do that? And similarly, let's say the tangential velocity would be r omega over radians. Okay, now why would it maybe be better to write it this way? Let's look at an example. Say we have this object moving in a circle that has a radius of, say, 10 centimeters, and it's rotating at a rate of 4 radians per second. We want to know the tangential velocity of a point right at the edge of this disk. So if we plug this in, we'd have r omega, so we'd have 10 centimeters times 4. If we plug in radians per second, we have 10 centimeters per second, which is a velocity, but then times this radian. And usually what we do is we would just write, we kind of say that that just a number by itself is automatic, or an angle is just assumed to be in radians unless specified otherwise. So let's say you have a 90-degree angle. You could write that as 90 degrees, or pi over 2 radians. But usually we just write pi over 2 and not include the radian. And so if you see an angular variable with just, the radian is kind of just assumed. And if you're not in radians, then you have to put a symbol there. And so if we don't include this unit here, then these equations work fine. And again, I've thought about writing that kind of so the units would work out. And also as a reminder that these equations are only valid if you're in radians, but they're generally not. I've never actually seen anyone else write them that way, so I'll stick with what everyone else says. But yeah, the idea is you don't plug the radian in. It's just if you have an angle as just a number, that's assumed to be radians. At this level, that might not, you're probably more used to working with degrees, but farther you go, the more you get used to dealing with radians. So our standard is we'll just write the number itself with no units involved. Okay. Now we can also talk about centripetal acceleration. So remember the centripetal acceleration is the tangential velocity squared over r. And the tangential velocity is r omega. So we can also write the centripetal acceleration in terms of our angular velocity. One of the r's canceled out, and we get the centripetal acceleration as r omega squared. So again, that's nothing new. You can just have v squared over r. But sometimes if you don't know the velocity, but the radius and how fast it's spinning, you can always calculate the velocity if you need to. But if you just want the acceleration, you can just plug it directly in with that equation. Okay. Now, a special case, let's say alpha equals 0. That would mean there's no angular acceleration. So it's spinning, but it's not speeding up or slowing down. And in that case, we see our tangential acceleration is 0. But the centripetal acceleration is not. So, in general, this object has an acceleration. And we look at, the tangential and centripetal. Those are just the components of the overall acceleration. The centripetal acceleration keeps it moving in a circle. The tangential acceleration changes its speed. Or you can think of the centripetal changes the direction, tangential changes the speed. Okay, so one more thing we have to talk about here. And that is a rolling object. And this marker's dying as well. Okay, so let's say we have a rolling wheel. Now we can talk about, say this is attached to a car. So you're driving your car, and if you're going 30 miles an hour, it kind of makes sense to say that your tires are also going 30 miles an hour. But it's not necessarily quite that simple because the tire is spinning as well. Every point on the tire is spinning except for the center. So the center is that one point that's just moving along with the car. But if you look at a point that's not at the center, it's going through this circular motion as well as a translation. And so we define the velocity of this object to just be the velocity of this rolling wheel to just be the velocity of the center of the wheel. And if it's rotating at an angular velocity omega, going through markers pretty quickly here. Alright, this one seems reasonable. We want to be able to describe this rolling object. So, again, this is a very important example because there's a lot of vehicles based on rolling tires. Or in general, just rolling objects. I don't know if I can get this to roll too well. It's kind of flimsy, but there's a rolling object. Now, let's say that you're driving and say it's winter and the road is icy. Is there an automatic relation between how quickly your tire is spinning and how fast the car is moving? And the answer is actually no. Like, you can imagine if you hit the gas, your tires are spinning very quickly, but the car is barely moving at all. So that's something that's very possible. And or if you're driving and your tires are spinning quickly, you hit the brakes and your tires can lock up, but the car doesn't stop because of friction. But most of the time, we're dealing with a case called rolling without slipping. And that's typically what happens. If you just go, if you watch any object rolling, that's probably what it's doing. Another possible exception to that is if you're playing pool. Sometimes you hit the ball in a way that it not only moves across the table, but spins either forwards or backwards, relative to the table. But we wanted to find what this condition, rolling without slipping, means. And I'm going to look at this point in contact with the ground. Let's call that point A. And rolling without slipping means that the velocity of point A with respect to the ground is equal to 0. So how is that the case? Well, here's our spinning object. If it's just in place, and not exactly a fixed axis of rotation, but you get the idea. This wheel's spinning, say, at a constant rate. And if you look at the point on the bottom, that point is moving to the left. And so if the object is moving to the right and spinning at the right rate, its point relative to the ground will not be moving. So when we're rolling, like this point on the ground is moving to the right because the whole thing is moving, but the spinning is causing it to move to the left. This tangential velocity equal to r omega. On the bottom, that would be pointing to the left. And so our condition, rolling without slipping, that means this point that's in contact with the ground, the velocity relative to the ground is 0. Okay. Now, I was just looking at my notes. I actually labeled it in the notes differently. I called point A the top and point B the bottom. So just to be consistent with the notes, let me change that. Got a better marker now anyway, so it'll be a little clearer. So let's just redraw this. So point C for center. And for now, let's call this velocity of the center with respect to the ground. So if you're driving 30 miles an hour, that would be the velocity of the center of the wheel with respect to the ground. And this is point A, and this is point B. So rolling without slipping means velocity of B relative to the ground is 0. Now I'm going to draw a few vectors here. So what these are, remember our subscript, first subscript refers to the object. So in this case, like point A, and the second is the reference frame. So this would be the velocity of point A relative to the center, and this would be, it's pointing to the right because we're spinning this way. The wheel's moving this way, it's spinning this way. So the tangential velocity is always perpendicular, and it, so it'd be perpendicular to the radius and kind of pointing in the direction that it's spinning. So on the bottom, it's spinning this way. Our velocity is to the left. And so we have to go back to chapter 3 when we were talking about relative motion. So let's look at this here. Velocity of B relative to the ground. It's a vector, even though everything is like, say, in the x, along the x-axis. Now we don't really need the arrow, but we can say the velocity of B relative to the ground is the velocity of B relative to the center plus velocity of the center relative to the ground. So let's check our subscripts. We start with B and with G. Two in the middle are the same. And so if we're rolling without slipping, this is equal to 0. So what that tells us is that, let's say the velocity of the center of ground is 10. Velocity of the center relative to the ground is 10 meters per second. That means that the velocity of B relative to the center has to be negative 10 meters per second. Because we're adding these two vectors. C relative to the ground, that's this vector pointing to the right. And B relative to the center is pointing to the left. And so we can just add them, add the magnitudes, because they're on the same line, except, this one's negative. So if velocity of the center with respect to the ground is 10 meters per second, then the velocity of B relative to the center is minus 10 meters per second. Or, it has a magnitude of 10 meters per second, but it's to the left. So let's do it this way. Let's just say magnitude and forget about that. And there's nothing really special about point B. Because remember, it's a circle. Point A is moving at the same speed relative to the center. So we can say, in general, the velocity of any point relative to the center is equal to the velocity of the center relative to the ground. So let me label this point E. So we're just talking about magnitudes here. So again, this would be a vector pointing in this direction, but the magnitude would still have to be 10 meters per second. Relative to the center, that's like if you have a spinning wheel, if you're just like running alongside the car, the tire seems to be in place but spinning. And every point on the edge has the same magnitude. So relative to the center, it's always 10 meters per second, no matter where you are. So we know rolling without slipping gives us this relation, but it has to be the same everywhere along the edge of the disk. Okay. Now, what if we want, say, the velocity of A relative to the ground? Well, let's do what we did before. Velocity A relative to the center plus velocity of the center relative to the ground. Now, notice these two vectors are pointing in the same direction, and so the magnitude of the velocity of A relative to the ground would be 20 meters per second. And I'll write down velocity of B relative to the ground as well. I mean, we already have it up there, but I guess we don't need the magnitude if it's 0. But anyways, yeah, it's actually a really nice picture I saw And they can find it and post it in this rotational, this module. But someone took a picture. There was a kid riding a bike, and they had like the shutter speed just right. And they took a picture of the wheel, and if you look at a wheel, it has spokes. But on the top of the picture, it was very blurry. But at the bottom, you could very clearly see the spokes. And the reason why is the person holding the camera is on the ground. And so, velocity of point B on the ground is 0. So this point here, like this spoke here, is not moving relative to the ground, but this spoke, near the top of the wheel is moving fairly quickly relative to the ground. And so, if you take a picture with a camera, the shutter has to open and close. And if you take a picture of something that's moving, it can certainly be, the picture can be blurry. If you go back to like when cameras were first invented, if you wanted to get a picture of yourself, you had to remain like as motionless as you possibly could for something like 10 minutes or several minutes. Otherwise, the picture would be very blurry. Nowadays, of course, they have cameras that can do this very quickly, so that's not as much of an issue. But so that was anyways a cool picture. I'll see if I can find that and then maybe just post it or in the module. So I'll double check and make sure. Yeah, I think that's it for this topic then of rotational kinematics. This is actually it for chapter 8. This was a short chapter. And we're kind of following what we did before. So this topic, we are looking at kinematics, just describing motion, just like we did in chapter 2. And then in chapter 4, we started talking about like what causes motion in the first place. And now we're going to ask what causes rotations next. So that'll be the next topic.